Alright, this is Ms. Robinson again, continuing with that example 1 on section 4.5. So if we move on to 1b in section 4.5, we see that we have a new rational function, x squared minus x minus 12, all divided by x squared minus 1. And we're going to follow the same steps that we followed last time. So let's start with step 1. So if we look up at step 1, we see that we need to factor the numerator and denominator of r. Okay, so let's look at our numerator first. So our numerator, x squared minus x minus 12, we would see that negative 4 and positive 3 multiply to give me negative 12, and can add to give me negative 1. So I would factor this into x minus 4 and x plus 3. Numerator taken care of. Let's look at our denominator, x squared minus 1. If I recognize, I see that this is a difference of squares. So I can make this x plus 1, x minus 1. Okay. And now I see that everything has been factored out nicely. I can continue on with step 1. Do not forget we still have the domain of the rational function as a part of step 1. So we want to look at our domain. So we remember that domain is where our x gives us issues, or wherever our x does not give us issues. So if we see here, we know that our denominator would give us an issue wherever it is equal to 0. And we see that that would happen wherever each factor equals 0. So at negative 1 for this factor and positive 1 for this factor. So I would say all x where x does not equal negative 1 or positive 1. And if I want to write this in interval notation, I could also say from negative infinity to negative 1, union with negative 1 to 1, union with 1 to infinity. So everywhere excluding negative 1 and positive 1 for x. Okay? Good. Moving on to step 2. So step 2 asks us to write our rational function in lowest terms. So we look back to our rational function for step 2, and we ask ourselves if there's anything we can cancel, simplify. We see here that we have no common factors between the numerator and denominator, so there is nothing to cancel. So we are at our simplified lowest terms. So I can just rewrite this, x minus 4 times x plus 3 over x plus 1 times x minus 1. Simplified. Okay. Moving on to step 3. Step 3 is to locate the intercepts of the graph. So we want to start with our x-intercepts. X-intercepts we know are where y equals 0, which we know is where our numerator equals 0. So we test each factor in our numerator for where it would give us 0. We see that this factor would give us a 0 at x equals 4. And this factor would give us a 0 at x equals negative 3. So our x-intercepts 4 and negative 3. Y-intercepts, we know our y-intercepts are where x equals 0, so we need to plug in 0 for x. So if we plug in 0, that's 0 minus 4 times 0 plus 3 over 0 plus 1 times 0 minus 1. This is negative 4. This is positive 3, which gives us negative 12. This is positive 1. This is negative 1, which gives us negative 1. So we see we have a y-intercept at positive 12. Alright, I've run out of room on the front of my page of notes. So if you still have room, continue. If not, flip to the back, take out a different sheet of paper. You do need to write this entire problem down. So please continue wherever you have space. I'm moving to the back side for my step 4. Before we move, let's look at what step 4 asks us to find. So step 4 asks us to locate the vertical asymptotes. Okay. So step 4, vertical asymptotes. I remember that my vertical asymptotes are where my domain gives me issues, where I cannot have my x values. So if we look back up here, when we find our domain, we saw that we could not have x equal to -1 or +1, so this gives me my vertical asymptotes. So I would say that I have a vertical asymptote at x equals 1 and at x equals -1. Again, we're being very careful to make sure that these are lines, equations, not just numbers. It's not just 1, it's not just -1, it's x equals 1 and x equals -1. Okay, those are my vertical asymptotes. So that's step 4. Let's go back to step 5. Step 5, first part, is to locate the horizontal or oblique asymptotes. Okay, so step 5. Either a horizontal or an oblique asymptote. Okay, so we decide if we have a horizontal and oblique asymptote depending on the degrees of our numerators and denominators. So if we remember, our function was x minus 4 times x plus 3 over x plus 1 times x minus 1. Or, before we factored, x squared plus 4 over, oh, sorry, wrong problem, x squared minus x minus 12 over x squared minus 1. Okay, so that was our rational function to keep in mind as we find a horizontal and oblique asymptotes. We remember for horizontal and oblique asymptotes that we need to divide our function if we have an improper fraction, meaning that our degrees are either the same or the degree of our numerator is larger than our denominator. Okay. We see here that our degrees are the same, so we should just divide them, still an improper fraction. Okay. So we take x squared minus x minus 12 as our dividend and divide it by x squared minus 1. X squared goes into x squared one time. 1 times x squared is x squared. 1 times -1 is -1. Subtract all of that and combine like terms. So I have x squared minus x squared is 0. Negative x, only like term. -12 plus 1, -11. X squared does not go into negative x, so that is my remainder, negative x minus 11 over x squared minus 1. Okay. We remember that our quotient gives us our asymptote. As it is just a number, we have a horizontal asymptote at y equals 1, the full equation y equals 1, and we do not have an oblique asymptote. Now, there is a second part of this equation, or of this step. Step 5 also asks us to determine points, if any, at which the graph of r intersects these asymptotes. So we need to figure out if our function will ever intersect this asymptote. Okay. So I need to ask myself, is there any moment where this function will equal 1? So I'm going to take my function and set it equal to 1. Okay, so I'm going to say 1 equals, and I'm going to use my original that's not factored, x squared minus x minus 12 over x squared minus 1. Okay. Get rid of that x squared minus 1 by multiplying both sides by x squared minus 1. Over here I have x squared minus 1 equals x squared minus x minus 12. And then I need to simplify. So x squared minus x squared, those would cancel. Combine my like terms here by adding 12. It gives me 11 equals negative x. Divide by -1 and I get x equals 11. I'm sorry, -11. Do you notice anything about what I had left over here after I started simplifying? If you notice, this negative x and this 11 is exactly identical to if I had set my remainder equal to 0. Okay. So if I had just originally taken my remainder, negative x minus 11, and set it equal to 0, then I would see that I would also get x equals negative 11. Okay. Both are fine ways of doing this. This is a more conceptual way of understanding why this is happening. This is somewhat of a trick. You may use either method. My suggestion is to make sure you understand why you are allowed to use that other method. Okay. Either way, we have x equals negative 11 as our intersection. However, we know that we have an intersection at a point. So if we remember, this is x equals negative 11 when y equals 1. So I have an intersection at negative 11 comma 1. So that gives me a point that I can plot later. Alright, so that's step 5. Step 6, if we remember, is to graph a rational function using a graphing utility. Okay. So I'll take my graphing utility, clear out everything I have from before, and then graph my function. Remember, we want to use the original function in order to check our work. So we are going to want to graph x squared minus x minus 12 divided by x squared minus 1. Now, you have to be really careful with your parentheses here. Not only do you need the parentheses on the numerator, but you also need those on the denominator because you are dividing by the whole function of x squared minus 1, not just x squared, not just negative 1. So you need to make sure that you're very careful with your parentheses. Okay. Let's graph it. Okay. So we have two functions here, but it seems like I'm missing something. I know in the middle here somewhere, I should have something being graphed, right? If we remember, we did have a y-asymptote. A y-intercept. We had a y-intercept at y equals 12. So I need to fix my window here so that I can see that y-intercept. So I need to know that I need to go to at least 12, but what this graph is showing me right now is that all of my values are above 10, meaning they're probably all above 12. So I should go considerably larger than 12, maybe 20 for instance. And let's try to graph this now and see if we get anything better. Alright, so now I'm seeing a parabola shape in the center here that I did not see on my graph whatsoever before. So it's really important that we change those values to see what's occurring in our function. Now, here, I can't exactly see what's happening, right? So I'm going to change my window there too. Now, I don't really need to go to negative 10 for my y minimum, so I'm going to go maybe to negative 5. Now, I also remember that I should have an intersection of my horizontal asymptote at x equals negative 11. So I might want to include this value on my graph so I can see this happening. So maybe I'll go to negative 12, my x-min, just so I can really investigate that these things are happening. We'll graph this. We can kind of see that happening at x equals 1. Over here, I want to see more of that side too. So maybe I'll go to 10 over here, just to check that that side doesn't intersect. Much better view of my graph. I can definitely see that this side of my function is increasing more than this side of my function at least. We can also use our table values to double check. So if we go to our table, if we go here, we see our error at 1 just like we should since we have a vertical asymptote at 1. We should also see it at negative 1 since we had a vertical asymptote there as well. Now let's look at our values. So there's our y-intercept at x equals 0, y equals 12. So that's good to see. we want to check that as we approach infinity or x equals positive infinity, we are not hitting that 1 value. So as we move to the right, we're not hitting 1. And if we scroll down our x values, we can see that we are getting closer and closer to 1, but it doesn't seem that I'm exactly hitting it. Let's go the other direction. So we know that as we approach negative infinity, we do hit that 1. We see that at x equals negative 11, we should have that 1. So if we go to negative 11, there we see it, y equals 1. So we're right about our intersection. Okay. So I want you to remember that your graphing utility is a tool to help check that your other answers are right. So when you're doing these problems, just because you wrote answers down on your paper does not necessarily mean that you should stop there. You might have made a mistake, they might not be correct, but you have this amazing utility at your disposal in order to check that all these things are correct. So you can check your asymptotes, you can check your holes, you can check your oblique asymptotes, you can check your intersections, all of these things you can check using your calculator. Mathematically, you should have these things on your paper, but you can always check and make sure that you have the correct answer before moving on. Okay? Alright, so we've graphed. All that's left is to write down the window we used. So the window we decided on, we had an x min at negative 12 and x max at 10, y minimum at negative 5, and y maximum at 20. Okay, so that gives us our window. Last step, step 7, we remember is to use the information from above to graph our rational function. Okay, so we make our graph here. Beautiful. Okay. And then we work our way down. So we go back to our original information. We look at our domain. We should not have negative 1 or 1. We look at our intercepts. So I need to plot an x-intercept at 4 and negative 3. So positive 4, label that, negative 3, label that, and then I should also have a y-intercept at 12. Let's spot that y-intercept. And label it. That's really all the information we had over here. Let's look back up here. We see we had a vertical asymptote at x equals 1 and x equals negative 1. Well, let's graph those. So x equals 1. Now the moment we write this dotted line, we should label it x equals 1. Same over here. The moment we draw it, label it x equals negative 1. So those are our vertical asymptotes. And then we move on. We remember we had a horizontal asymptote at y equals 1. So we should add that as well. Okay. Label it y equals 1. Alright. But then we saw that we had an intersection at negative 11. So we're going to plot this as well. Okay. So we have that point at negative 11 comma 1 where it intersects our graph. Alright, now we can start to use this information to graph some actual lines. Okay, so let's start with each part of our vertical asymptote. So each part that's been chunked off. So we look at this far right side here. We know we should either go above or below this horizontal asymptote since we know it does not intersect over here. We see that we have an intercept here, so we must cross over here, which means we must be below here. Okay, so I can draw my graph as such. Plug in more points if I want more accuracy. This is enough. And then I can move to the center. Now we remember here, we cannot cross this. We might want to plug in some values in between here, but since we cannot cross this, we know that our graph should move above. So we should see that it is some sort of parabola moving up in both directions. Okay. Then we move to this far left side. Now this time we know that we intersect this horizontal asymptote. We know we cannot intersect this vertical asymptote, so if I follow this idea, I should be moving down this way towards my vertical asymptote, and then slowly up in this direction. Okay. So we labeled all the points, we labeled all the asymptotes as we went, so make sure that you are doing this. Make sure that you reference what you graphed before as well in order to double check what you're doing here. Okay. Always a good idea. Alright, that is it for example 1B. Thank you. I will meet you again for example 1C.